I'm Larissa Jones, and I did my part on the DNS section, and the values I got for the DNS were from the DNS.time field in Wireshark.
My name's Kimberly. I did the HTTP analysis. So the server we used encrypts packets using TLS, so I did my analysis on a different file. I got the latency of the HTTP request response by taking the difference between response time and request time in Wireshark.
I'm Spencer Lanfried. I did the TCP analysis of our file retrieval. To calculate the TCP idle time or stall time, I manipulated the Wireshark trace data and extracted information from each individual TCP segment. And using this information, I could calculate the idle time by pairing the idle time or the response time from the first TCP segment to the last. And I repeated this for every single TCP stream in order to calculate the plot for my data.
So the file we used was studentqrg.pdf, which was 430.5 kilobytes, and it came from the server researchlog.grad.ucl.ac.uk, which is located in London, England.
The DNS requests used UDP on port 53, and the requests were sent to IP address 152.19.240.8, and it was done using recursive queries. There were 4 requests and response in total, with the first one being for researchlog.grad.ucl.ac.uk, where the length of the response was 289 bytes, the type was type A, and the time it took was 98.046 milliseconds. The second request was for ocsp.tcs.terrana.org. The length of the response was 399 bytes. It included both type A and type C name in the answer section, and the time it took was 121.416 milliseconds. The third request was for ocsp.usertrust.com, with a length of response of 367 bytes, type A, and the time it took was 5.032 milliseconds. Finally, the last request was for researchlog.grad.ucl.ac.uk, with a length of response of 289 bytes of type A, and the time it took was 97.243 milliseconds. All of this added up gives for a total latency of 321.737 milliseconds. The method I used to get this information was from using the packet information on Wireshark. Within the packet information is a field called DNS.time, which gives the time between the query and the response, i.e. the time it took for the DNS request to finish. This is the time that I used for the latency. I was able to complete a DNS trace on the URL that we used and saw that it first went to a root server of b.root-servers.net, from which it received information to lead it to nsb.nic.uk, which was for the UK ending, which then gave it some responses that led it to ns4.ja.net. And finally, it got a response from that led it to bas-a.bbc.ac.uk, which gave it a record for the website. And in total, this DNS trace took about 200 milliseconds.
This is the HTTP analysis. As I previously mentioned, the file retrieved from the server we used was TLS encrypted, so I carried out the analysis using a different file so I could see there were requests and responses in plain text. A little bit of background about the file I used. It's a zip file containing an animation program, and it's about 5 MB in size. I downloaded it from a Geocities site hosted on a server in Tokyo, Japan. So I started Wireshark at time equals 0. The HTTP request was issued at 3.22 seconds after Wireshark was started. The 200 OK response was received at 3.43 seconds, and the file finished downloading at 7.81 seconds. So the total HTTP request response latency is measured as the difference between when the HTTP GET request was sent and when the final continuation HTTP message was received, which is approximately 4.589 seconds. So the HTTP response came as a series of continuation responses, basically because the file was too large to fit in a single TCP response packet. So a continuation basically means is that the file is still in the process of being downloaded. This graph shows the series of continuation responses that was received, where the x-axis is just like the cumulative number of responses received, and the y-axis is the same as the graph on the left-hand side. It's time. So the continuation response is designated as a HTTP message, but it doesn't actually contain status code, a message, or any of the usual headers. This is the HTTP GET request sent by the browser. The client is running on HTTP 1.1. Its IP address is 152.23.65.188, and it accepts English US and English responses. This is the HTTP response sent by the server. The server is also running on HTTP 1.1. Its IP address is 118.151.231.180. The status code it returned is 200 OK, and it's saying that the size of the file is approximately 5 million bytes, which is also about 5 meg, the size of the file. These are some of the questions from the retrieving long documents part of the Wireshark HTTP tutorial. In response to the first question, one HTTP GET request was sent because only one file was requested. 3,851 TCP segments were needed. I got this number by exporting the Wireshark data as a CSV file. Using Excel, I filtered for TCP packets coming from the server's IP address, where the sequence number came after the HTTP 200 OK responses. And so I found 3,851 segments. The status code associated with the response is 200, the phrase is OK. And there weren't status lines in the TCP-induced continuation because continuation isn't actually a HTTP message.
To begin my TCP analysis, I had to manipulate the Wireshark trace information in order to extract times and values that would help me calculate the TCP idle time for each connection that our file retrieval process made. Firstly, under each TCP segment, there is a data field called time since first frame in this TCP stream. I made that a column, and next there's also a data segment called stream index, which I made a column, and combining both of these into a column allowed me to separate each TCP connection as its own block of trace data, and the time since first frame allowed me to see how much time had elapsed for each TCP segment in a specific connection. Now, to calculate the idle time for each TCP connection in our file retrieval process in our trace, I took the difference of the TCP ACK plus request time and the TCP's FIN segment time. By doing this, I was only looking at the portion of data that was dealing with object transfer, so I didn't include the connection and the closing times, and I could calculate the TCP idle time, or what I presume to be the TCP latency, as referred to in slide set 3F. And the graph before you shows that most of these TCP connections, the idle times were under 1 second. However, connection 14 had the largest idle time of 6 seconds, and I presume that to be the TCP connection that actually dealt with the file transfer of the object that we are retrieving from the server, because it's the spike in the graph with the largest time, which may correspond to more data being sent back and forth between the client and the server. My methodology I used, as I previously stated, was taking the time from the TCP ACK plus request segment to the TCP FIN segment. Thus, I'm not including handshake or connection time, only looking at total time of object transfer. And I also split it into multiple streams under my trace data because I wanted to evaluate each TCP connection separately. As extra analysis, I chose to calculate the recovery times of the losses for our TCP connections. So we had 4 losses. Our first loss, very simple. The server retransmitted the file immediately after TCP ACKed the loss. The recovery time was 0.29 milliseconds. The second loss was something completely different. I think the connection just timed out because there's no more segment data being sent after TCP client ACKed the unseen segment to the server. So the recovery time was 4.924 milliseconds until the connection timed out. Our third loss was like the first loss. The recovery time was 0.731 milliseconds, and the fourth loss was like the first and the third losses, and the recovery time was 0.546 milliseconds.